Swayam Prabha. Digital India. Educated India.
In this class, we will talk about something what is known as Cepstrum analysis. Well, by now you know that in the signals there could be sidebands because of modulation. Okay. We have just seen that sidebands could be because of frequency modulations, sideband because of amplitude modulation. In the case of amplitude modulation, I have the sidebands, Fc plus minus Fm, okay, and in the case of frequency modulation, I have Fc plus k times Fm, where there will be multiples of the modulation frequencies. Now, imagine if there are not one source of modulation, but there are several sources of modulations in a signal, particularly a multi-stage gearbox. So, there will be a family of sidebands. So, in a signal, if I have a lot of sidebands apart from the fundamentals, you can imagine the problem I will have in the frequency spectrum as to relate to which frequency or which sidebands came from which machine. Okay, that is the problem I have in front of me. Okay. So, this Cepstrum is a technique by which we can cluster a group of sidebands coming from one source as a single parameter. Particularly, Cepstrum for its utility, actually what happened in a Cepstrum is such a powerful signal technique, analysis technique, in which it can distinguish between sidebands very easily. A lot of this earthquake signals or seismic signals, they have a lot of sidebands. Human voice or speech signals, they have a lot of sidebands. Okay, to understand between different pronunciation, different words which are coming out of a human being, particularly for speech processing, Cepstrum is very, very useful. So, Cepstrum started, its origin is from earthquake signals and from human voice signals, and then when later on we as machinery diagnostic engineers found out that our gearbox signals also have a lot of sidebands. So, why not we use Cepstrum to understand more about these gearbox signals, for the fact that they can distinguish and identify different groups of sidebands coming from a gearbox. So, what is this Cepstrum? If we look into this equation here, it says that Cepstrum of a signal is the inverse Fourier transform, f minus to the power minus 1 is the inverse Fourier transform of the Fourier transform of a signal and its logarithm of that Fourier transform. Okay. So, because you are doing an inverse transform here, the Cepstrum is again back to the time domain. Okay. So, let me graphically represent this to you. Suppose I have a signal x t, I do its Fourier transform, I will get a signal x as a function of f, which can be written as x real as a function of f plus x imaginary as a function of f. Okay. Now, if this frequency signal has, for the sake of argument, has lot of sidebands, and these are the sidebands around a particular frequency, and then on top of it there will be noise. This becomes very difficult to understand, as you will see in an example I will show you. Okay. So, now if I do a inverse Fourier transform of this, I will get back Cepstrum in another time domain, and this is what is known as the Cepstrum. Well, how this is done? Because to do the inverse Fourier transform, because I am having a real signal, real quantity here, and I am having an imaginary quantity here. So, to do the inverse Fourier transform, you take the logarithm of the amplitude of this as the real part, and the imaginary part will be the phase. But this phase will always be from minus pi to pi. So, this will be a discontinuous function. So, to smoothen it, this has to be made a continuous function, and this continuous function for the phase is done by a technique which is known as phase unwrapping, and there are many algorithms available for doing this phase unwrapping. So, once I have this real and imaginary of the frequency converted, one, the real part being the logarithm of the amplitude and the imaginary part being the continuous phase. Once I have such an edited spectrum, then I do what is known as the inverse Fourier transform to go back to the frequency to the time domain. Now, in the time domain, what happens? Because if you look at Cepstrum, the way it comes, it is just the spectrum C replaced by S. Okay. When we had frequency as the x axis in the spectrum, here it will be, it is known as the Q frequency. Okay. So, I will get different Q frequency here. Now, this Q frequency, I will get certain peaks here. Okay. Now, this is in time domain. So, say suppose this is t1 time, okay, and then say this is t2 time. F1 will corresponds to 1 by t1, F2 will corresponds to 1 by t2. So, if there is a high amplitude at a particular Q frequency of t1, that means in this spectrum I had high amount of sidebands at frequency f1, because otherwise it would be very difficult. If I go back here, it would be very difficult. I will show you an example. It will be very difficult to find out which frequencies are predominant, which sidebands are predominant from such an FFT analysis. Because FFT analysis, for our class we have seen in a nice pure tone and nice mathematical functions, we get neat Fourier transforms. But in reality, once you go to the machines, we will have so many unknown frequencies, it becomes very difficult for us to find out which frequencies are present, which are the defect frequencies and so on. So, if I do this Cepstrum, I can find out whether F1 is strong enough or F2 is strong enough or F3 is strong enough or so on, okay, depending on as many Q frequencies you have. Now, question is, you would have seen FFT can be done by the n log n algorithm, and it can be implemented in real time. Okay. Unlike FFT, Cepstrum cannot be done in real time, because a block of data has to be taken, they have to be processed to find out their log amplitudes, they have to be processed to find the unwrapped phase as a continuous signal. So, once we have an FFT, then once you go for a Cepstrum analysis, there are software who will do this calculation for you, but then it is not real time, it will take some time for computation. Once such computation is done, and then once you do this Cepstrum, you will see the harmonic, the amplitudes or the harmonics as they are called at different Q frequencies, okay, and then you can find out whether a particular group of sidebands is present or not. Another effect of Cepstrum is it deconvolutes or removes the effects of the path, because if the two signals are convoluted, you will, or the effects are there. Suppose a signal x multiplies with signal y, okay. But if I take the logarithm, because I am taking the logarithm, it will be log x plus log y. So, the effect of the path is actually added to a signal, which can be nicely removed once you do Cepstrum. So, that is why Cepstrum had an important application in seismic analysis of signal, because if an earthquake occurs, the signal which is recorded by us is signal x times signal y. Y could be because of the path from the epicenter of the earthquake to the location where your transducers were put. So, these effects could be added and removed, and their effects can be eliminated once you do Cepstrum analysis, because of this logarithm property of the property of logarithm. Okay. That is another advantage of Cepstrum analysis, but here we will see same also happens. Suppose I have a large gearbox, lot of signal contamination occurs because of the path, whether it is coming from location bearing through bearing A or through bearing A, B, C, all those effects will be lost or easily removed once we do Cepstrum. So, to summarize, Cepstrum is a powerful method to find out sidebands in modulated signals. Now, we will go to one example wherein we will see how Cepstrum analysis helps us diagnose the fault in a cement plant. If I was to show you here, actually what happens in a cement plant, this is a large rotary kiln. Okay, this is about, if I was to explain you the cement plant here, this is a kiln wherein all the mixtures for making the cement, the mortar mix, the limestone, the etc., they are put in this drum, and in this drum there are very, very hard stones or rolling kind of rocks, which will be, it is like a tumbler, and this drum, this diameter could be about 2 to 3 meters, okay, this diameter, and this length could be about 7 to 8 meters, and this there is a small inclination between this feeding end and the delivery end, and this could be about 2 to 3 degrees slope. So, you put in the raw materials, and the beauty of this is, the unique part of this this drum rotates at about 2 to 3 RPM. It rotates very, very slowly, and this media along with this grinding media along with this feed is mixed, and finally, end of here you will have the dry cement powder coming out. Okay. Cement mixing, cement manufacturing is very easy in that sense. If you have the right proportions of the ingredients, you just grind them and you will get cement powder. It could be a mixture of fly ash, limestone, gypsum, etc., and then you just grind them. So, this is nothing but a grinding mechanism, and same also happens to your your washing machine detergent, etc. They are also manufactured in the same process. You will have some ingredients, they could be temperature controlled, and then you have a grinding media. But from a mechanical engineer's point of view, you see that this is running at 2 to 3 RPM, and I have this big motor here. This could be about 900 horsepower. This motor is running at about 1200 RPM or 1400 RPM or 2800 RPM. That depends on the number of poles in the motor. So, obviously, from 1400 RPM, if I was to go down to 2 to 3 RPM, you can imagine the amount of speed reduction required in this gearbox. So, a very critical thing in such a cement plant is this gearbox. So, this gearbox is a heavy gearbox with such a large speed reduction. Obviously, I cannot get such large speed reduction in just one gear. So, there are intermediate set of gears, okay, and they are helical gear, they can take a lot of load and so on. And then we have this gearbox which is having the speed reduced, and then we have sometimes this speed is also not to 2 RPM. We have another which is known as the bull gear here. All around the drum there is the ring gear, and then there is the pinion gear, and then finally, this brings about the speed reduction. And then, so that the there is a torsion shaft here, and this is the weakest member here. So, if there is any failure, the torsion shaft will shear and fail. Okay. This is just a safety measure, in the sense we do not want any of the bearings to fail or the gears to fail, but just let this torsion shaft shear. Okay. And then they can take in a lot of sometimes this is held by plumber blocks here, and the problem here is this bearings in this gearbox. Suppose I put a transducer here, they will be capturing phenomena of all the gears, capturing phenomena of some of the gears here and bearings. So, now question is which bearing has a fault, and that is what, if you do the analysis, you will see that the same problem occurs, that which sideband corresponds to where and how do I find that. So, this is just to give you a small example of the dimensions of this plant. This drum has an OD of 2500 millimeter, ID of 2350 millimeter, and it is 12 meter long, and it weighs about 70 tons. You can imagine the magnitude of the cement plant mill or the drum. The girth gear has 150 teeth, the girth pinion has 21 teeth, the girth gear or the ring gear, okay, and then there is the speed reduction from 21 teeth to 150 teeth. The torsion shaft has an ID of 395 OD of 395 OD. There are a couple of gear couplings, and in this gearboxes there is a pinion, gear, and all these different modules are there, and the number of teeth are also mentioned here. If you can read that, 17 teeth in the gear stage 1 pinion, 61 teeth in the stage 1 gear, 22 in the stage 2 pinion, 34 teeth in the stage 2 gear, and then you can work it out. The motor is a 3-phase induction motor with an 600 kilowatt, and it runs at 985 RPM, and bearings for location 3, 6 are given, and then the just for your benefit, the grinding and mixture material in drum is about 39 tons is the mixture material. So, we get about 4000 kg of cement in it, because this 39 tons is the weight of the grinding media, and then the cement raw material flow is about 12 tons per hour, and the drum filling ratio is about 25 to 40%. Drum is of course not entirely filled, it is like a hollow drum which is churning with this grinding media and the raw material. So, we are getting about 12 tons an hour of cement from this plant, okay. And this is what it is there in a cement plant. So, as you will realize, be it a cement plant, be it a detergent plant, this gearbox is very critical to the plant. If this gearbox fails or if this motor fails, the plant is shut down. Okay. And this is some of the views of this the torsion shaft, and this plant is very close to us. We had done some measurements there after a failure, and then we had to do a diagnosis also. This is the pinion, and this is the drum which is rotating. Okay, this is the other side, and the ring gear or the girth gear is inside this enclosure. Okay, and the pinion is here, and this is the torsion shaft, and this is the gearbox. Okay, this is the motor here. So, motor is driving the input stage, intermediate stage, and then this side goes to the torsion shaft. And because of the, I would say, defects, because of obvious reason there are certain defects. So, we put accelerometer at the bearing locations, accelerometer near the foundations, and we had taken the measurements of this vibrations simultaneously. And obviously, this measurements cannot, this analysis, as I was telling you, Cepstrum cannot be done real time on the fly. So, we have to record the signals in a DAT recorder, wherein you can record almost 8 channels of vibration simultaneously to a bandwidth of 20 kilohertz. You can record them in the step, and then because in such a dusty environment, we cannot be, because cement dust, if you go to that plant, a lot of cement dust everywhere. We cannot be putting computers and sophisticated equipments and then doing an analysis setting to a area of cement dust. So, all you do is you just record them in that media, bring them to the lab, and then use your softwares of MATLAB. You can be doing FFT, and then do this Cepstrum analysis as per the algorithm I just mentioned. And then of course, another study which we did just to see the dynamics of the bearings. This is another view of the cement mill. Is this is the stage 1 pinion, the rotor shaft, the compound gear train, torsion shaft, girth gear, and this is the drum. So, you can imagine the dimensions of the problem. Okay. Now, these are the vibrations of the cement plant at different locations, and all I have shown you here is this spectrum. These are just the FFT spectrum, and these are real FFT spectrum obtained from the 8 different locations on the cement plant while the operations were going on. And if you look at any one spectrum, it becomes very difficult for anybody to find out which kind of sidebands are there. And if so this is very difficult for us from a signal analysis point of view to find out the group of sidebands. So, this is just to tell you the severity of the problem we have in hand. So, now this is the vibration spectrum. The top one is the vibration spectrum. This is in kilohertz near the bearing of the multi-stage gearbox, and then you will see a group of sidebands occurring. Okay. And then I would not know. So, if I come to the second plot here, they are all in time domain, and if you look here, the corresponding frequency will be shown, and you will know, well, this corresponds to a particular rotational shaft of the gear, and then we will know its frequency content, and from this frequency we will know, well, this means this has a high amplitude, means this is the strongest sideband, and that is what Cepstrum helps us in. I will give you another example here just from this gearbox. See, suppose I have a pinion. Okay. So, this is having 20 teeth, and so this is having 50 teeth. Suppose this is running at 1200 RPM, and this corresponds to 1200 by 60, that is 20 hertz. So, this will be running at a speed of 20 into 20 by 50, that is equal to 400 by 50, that is equal to 8 hertz, right. So, the gear meshing frequency is nothing but n times T1. This is 20 times 20 times 8 times 50, that is 400 hertz. Now, suppose for the sake of measurements, I put this set in a gearbox. This is the gearbox casing, and I put one transducer to do the measurements. Okay. It may so happen, if I look into the time history of the signal which I have measured, I will get something here, but at most the analysis I do in time domain is I can find out their RMS, mean, kurtosis, etc. But this will only give me a relative measure of the strength of the signal, and that is all. I cannot pinpoint whether my fault has occurred in a pinion or a gear. But if I do FFT analysis, what is going to happen is I may see an 8 hertz signal, 20 hertz signal, and few other signals, but what is going to happen is and this is very, very important. This could be 8 hertz. This could be corresponding to the rotational speed of the gear. This could be 20 hertz corresponding to the rotational speed of the pinion. This is the gear meshing frequency of 400 hertz. But what I will also see is the side bands around the gear meshing frequencies, and I will draw another family here. Okay. This spacing in one case will be 8 hertz, in another case it will be 20 hertz. Why has this occurred? Because modulation is there. Because of modulation, side bands have occurred. So, I have got a group of side bands. Okay. Now, this is very nicely drawn here, but if you go back to my actual measurement, and this is what it is looks like. It will be very difficult for me to find out. I may find out the gear meshing frequencies, but here other than the gear meshing frequencies, there will be frequencies coming from the bearings, frequency coming from many other machineries. So, it is very difficult for me to know whether the sideband is because of a pinion or because of a gear. So, the power of the Cepstrum is to identify which sideband is more strongly predominant. For example, in this gearbox, I will know if a sideband occurs at 8 hertz, that means I have signal coming from my gear. If my sideband occurs at the 20 hertz, I know this will be from my pinion. Okay. So, what is going to happen? If there is a defect, it may so happen that the amplitude of the sidebands around the gearbox is going to increase. The frequencies are not going to change, frequencies are fixed because of the phenomena. So, this amplitude of the sidebands will increase, and this is very nicely explained here, but in real world signal it will be very difficult first to identify the sidebands. Forget about whether to know whether they have increased or decreased. But if I do a Cepstrum, see the Q frequency and know, well, no, it is this frequency which corresponds to the pinion which is increasing, I can say for sure that the sidebands of the pinion has increased. So, pinion is at a fault, and that is the power of Cepstrum analysis. So, sometimes if you have done a good measurement, a good kind of frequency analysis, if you have a good delta f, you can do a good resolution, and then you may be able to distinguish them. But Cepstrum otherwise is a very, very powerful technique to determine modulations in signals. Okay. But this will be again complicated by the fact that while doing all these operations, suppose speed of your machine changes, then what is going to happen? We will have frequency smearing, okay, because once it was 1 hertz, say 10 hertz, next time it was 10.1 hertz, next time it is 9.1 hertz. So, instead of getting and then if you do multiple averages, instead of getting a sharp peak, you will land up with a signal like this. So, now you will be confused. Now, what has gone wrong with my machine? Is it this frequency? Is it this frequency? Is this frequency? So, this is very important. While doing all this analysis, we have to ensure that the speed is not changing, or otherwise we do what is known as the synchronous averaging, or which we do what is known as the order analysis. Or order tracking. By order I mean one rotation or one rotational speed, no matter what. So, it is the time taken to rotate by one revolution and its inverse. Okay. So, order analysis, if the speed is fluctuating, the signal will be taken for the complete revolution. So, we will not miss that, and that is something we will discuss in the later class. But in Cepstrum analysis, the advantage is it will detect the sidebands and also remove the effect of the path. So, if I was to go back again to the vibration spectrum of the girth gear support, this is how it is. The real world signal is full of so many frequencies, because this is the frequency domain. it becomes very difficult to identify well whether it is this frequency and so on. Okay. But once you do the Cepstrum, you will see the important group of frequencies getting clustered into this Q frequencies. Okay. So, again in MATLAB, the software which we are using in our class, you could look into the commands like Cepstrum, Cceps. Okay. If you do not take the logarithm of the amplitude, now you may also land up with different forms of the Cepstrum, whether it is a complex Cepstrum or a magnitude Cepstrum. So, there are many ways by which people represent the data out of a Cepstrum. Okay. And sometimes they call it as a power spectrum. If you are dealing with a power signal and auto power spectrum, then you will have a power Cepstrum. Okay. Because if there is a voltage square term or an amplitude square term, I can call it as an auto power spectrum. If I do a Cepstrum of an auto power spectrum, it will become what is known as a power Cepstrum. Okay. There are different ways of representing this data, but we can generate signals in MATLAB. I can briefly tell you how to generate a signal in MATLAB. For example, we can first is in MATLAB you can write your own M file, say for t is equal to if I take del t as say 0.001 hertz, that means Fs is equal to 1000 hertz. I can generate a signal x is equal to 10.0 sine 2.0 star pi star f say maybe 10.0 star del t star t. So, this will generate a signal x. Okay. I could modulate this signal by x m as (10.0) sine of 2.0 star pi star times sine of 2.0 star pi star. So, if you generate such a signal, I have a carrier frequency of 50 hertz, a modulated frequency of 10 hertz, a sampling frequency of 1000 hertz, a modulated frequency and then sampling frequency. So, once you do the FFT of such a signal XM, how do you do that FFT of such a signal FM? Suppose you write XF is equal to 2.0 by, suppose you have taken 1000 data points star absolute value of FFT of XM, you will get the amplitude in the frequency domain, and then in such a spectrum you will see the frequency of FC plus FM, you will see FC minus FM, you will see FC FM. Okay. And if you do the Cepstrum of this signal, you need not take the FFT. So, you have to look into the algorithm C Ceps of XF equal to XC Cepstrum of XF. So, Fx, this is in the frequency domain, and this is in the time domain. So, you will get all the signals which has which corresponds to, this will give you in the Q frequency. So, you will get the Q frequencies corresponding to the frequencies of FC minus FM and FC plus FM in the Cepstrum, and this you all can do in program like MATLAB. Okay. Now, if I was to come back to my example here, again look at the vibration spectrum and substrum at gearbox base. If you are just to compare the gearbox base, because of a very poor foundation, you see so many frequencies are coming up in the spectrum, and if I asked anyone to find out the frequencies contained in the signal, you will be all scratching your heads, getting lost, like what are the frequencies here. But the same spectrum converted to Cepstrum, you will see the group of sidebands coming up, Q frequencies clustered, sidebands clustered into their families, and you will see whichever Q frequency has the highest amplitude, that has a strong presence in that signal, and that is how Cepstrum helps us identify signals, helps us finding out the important frequencies in a spectrum. Okay. The effect of the path etcetera is lost, because if you look here at the gearbox base, lot of effects of the path etcetera was there. The gearbox base was loose. In fact, we had discovered many loosenesses in the gearbox foundation itself, and all those effects are nullified once you do the Cepstrum. Those effects can be easily removed. And similarly, when we did on the motor and gearbox only, we could see the spectrum of different natures altogether. Okay. And from this example, actually what happened, we could find out the characteristic frequencies of this signal which were not apparent in this spectrum, but once we did this Cepstrum, we could find out the characteristics Q frequency in the Cepstrum, and we could pretty well conclude that the bearing 2 was loose on the foundation, bearing 1 and the mill were misaligned, and pinion on the gearbox was damaged. In fact, later on we removed the gearbox, and subsequently it was reported that one of the pinions in the gearbox had a damaged tooth. Okay. So, this tells you how powerful Cepstrum is to actually not let you scratch your head when you see a spectrum from a real world machinery signal. Okay. Spectrum from a real world machinery signal has lot of frequencies which we may not be able to account for, okay, because of all I know is the defect frequency, but there are so many extraneous signals which could be from nearby machines, which could be from machinery parameters which I am not even aware of. But if I know I am looking for a particular family of sidebands, I can very easily do Cepstrum analysis and then see them as the Q frequencies, because one thing you should recollect, Q frequency is 1 by, or inversely I will not say 1 by, but is related to this 1 by the frequency. So, Q frequency is in time domain, usually in milliseconds, and this is in hertz. So, there has to be an inverse relationship. So, we have time to spectrum to Cepstrum. So, this is in the frequency domain and this is in the time domain. Of course, this is to okay, this is the relationship and this is time means Q frequency. And this of course okay. So, the effect of all the path properties are lost once we do Cepstrum. So, Cepstrum applications are also in speech, seismic, and then of course, in machinery diagnostics. This is not a real time operation, this is on a stationary signal. I may not be able to do Cepstrum on a non stationary signal. For example, one transient, it will be very difficult. Okay. But if this transient is captured, we can do some sort of an analysis of it. Okay. But this has given way to nowadays what is known as simultaneous or joint time frequency analysis, and there are few modern methods of signal processing like the wavelet analysis, short time Fourier transform, which has been nowadays used in machinery fault diagnostics, particularly for non stationary signals. But in this very preliminary or the first course on machinery fault diagnostics and signal processing, I will not be focusing on these aspects of signal processing, but just to it will suffice that there are methods available today wherein we can do analysis of non stationary signals by the wavelet analysis, short time Fourier transform, wherein the signal's frequency is changing from sample to sample, and then I need to know in 3 dimensions, as a function of time, as a function of frequency, amplitude. And these techniques are available, wherein we can see, for example, I will give you examples of non-stationary signals, something breaking, cracking, impulse, door slamming, etc. These are phenomena, something hitting, rubbing. This can be very easily understood by wavelet analysis. Wavelet analysis also, there are two types, discrete wavelet transform and the continuous wavelet transform, and then short time Fourier transform, because we can and then there are the multi resolution Fourier transform also. But we will not stress on this in this course, being the very first course in machinery fault diagnostics and signal processing. But these techniques are available nowadays in the literature, and people have been practicing them for using them in condition monitoring. And we will later on see some applications. When we talk about applications, how some of these techniques are used, particularly for fault diagnostics in bearings and gears and rotating machines where the shafts have cracks, etc., how these techniques can be used to find out their faults. Okay. Thank you.